Hey, this is Mr. Ariel. I'm here today with some Electron configuration practice. Now you should have a worksheet for this, so if you got it, let's go ahead and get started. So at the top of the page, we're just going to write out the Electron configuration of each element shown below, and I'll just get you started with maybe the first two, and then you'll pause the video, try the rest of the problems, and check your work. So for fluorine, I could go to the periodic table real quick and find that that's 9 valence electrons, but I'm not going to show you that part. You know how to do that pretty well. And so if I've got those 9 electrons, we're going to start on the diagonal rule. We start with the lowest energy level first, and that's 1s. And so we'll put those first 2 electrons into that 1s sublevel because it can only hold the 2 electrons. So keeping track, we had 9, so now we're down to 7. Next energy level to go to, or in the diagonal rule, is 2s. So that's going to be 2s, and again with a 2, because that's all it can hold. We're down to 5. And so following the diagonal rule, we go to 2p, and that level can hold up to 6 electrons, but we only have 5, and so that's going to be it. Now the next question, sodium, that's got 11 electrons. You can find that on the periodic table, and I do want to show you something to speed this up a little bit. If it's got 11 electrons, the first 9 of them are going to be exactly the same as the previous problem. So that's going to be 2p5, but I'm not going to write that 5. I'm going to write 2p6. So what I just did there, if I add up 6 plus 2, that's 8, and then plus 2 more, we just got 11. We're down to 1 electron that's left over. And so if I pick up on the diagonal rule, we're going straight to the 3s, and that'll be a 3s1, and that's where that element ends on its electron configuration. Now go ahead and try up to 8. Pause the video, and then come back and check your work. All right, now on this, definitely check your work and definitely look at this right here where that 3D level shows up, where it's a jump back from the 4 down to the 3D. Be sure you look at that. Now pause the video and check your work really thoroughly. All right, now that you're ready to move on, let me clean up the board just a little bit. Now we're not moving on to the problems at the bottom of the sheet just yet. There's one more thing we need to do with these 8 problems. Now if by number 8 you were thinking this gets a little tedious, what happens when you have an element and you need to write out the configuration, but it's got like 127 electrons? That would get really lengthy, and it'd be really tedious and easy to make a mistake. You're right, and chemistry has a way to deal with that. It's called noble gas notation. Make a note up in the top corner of your paper that that's using the previous noble gas, that's elements in group 18, to kind of shorten the configuration. Get that into your notes, but I want to show you what it looks like on the periodic table. Fluorine is right here on the periodic table, but if we kind of back up on the periodic table, the noble gas that comes before it is helium. And so I can come back to my practice problems and I can summarize the noble gas notation for fluorine. I can just write helium, put it in brackets, and what I'm doing here, this 1s2, that's helium's electron configuration. And so now I just need to write on the rest of the electron configuration for fluorine. So that's 2s2, 2p5. So for a real small atom like fluorine, it really doesn't do much to shorten things. But if on the next one, that's sodium, well, backing up on the periodic table to find the previous noble gas, that's neon. And neon encompasses all of this electron notation. So I can shorten sodium just by doing this, writing the symbol for neon, put it inside brackets, and then I just need to copy in the last part that makes sodium different than neon. So if you get that idea, I want you to pause the video and do the noble gas notation for all the way up to number 8. Now be sure you've got your answers checked on this, and let's move on. Now I know the periodic table is not actually on this worksheet, but get your copy. You probably already have it out. We need to make a few notes on it. If you didn't mark it on your periodic table during the notes that this is called the S block, I would do so now. And then these elements over here are called the P block. Remember, it doesn't really include helium. These elements right here are called the D block. And then these elements down here, that's called the F block. Also take some time to number right here, 1, 2, we're numbering the rows as they go down the periodic table. Make one more note on the D block that you count back by 1. And then for the F block, make a similar note that you count back by 2. Now the reason I want you to update your periodic table with this is because the diagonal rule is really helpful for getting started with electron configurations, but you're not always going to have it, and you're not always going to want to get that sheet of paper back out of your notebook. And the periodic table can tell you everything you need from that diagonal rule. Let's just write out the electron configuration of iodine right here. It's got 53 electrons, and we're just going to do it with the noble gas method. And to do that, I would identify the previous noble gas, that's krypton, so I'd put it in brackets, and then I'm going to pick up right over here with the next electron. Krypton's got 36, and so I just need to add on some information here for the electrons to get me all the way over to iodine. And so because I put a 5 here, and this is the S block, I've got 5s, and I know I've got at least 2 electrons here, so that's 5s2. And then I'm coming across to here, this is the D block, but I count back by 1, and so that's 4d, and I've got to go all the way across to here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Gets me to cadmium, so 4d10, and then I pick up right here with indium at 49, and that's the P block again, and so we're back up to 5p, and I'm going to go 1, 2, 3, 4, 5 to get to iodine. And so there you have it. That's the electron configuration, the noble gas configuration for iodine. Now moving back to something on the worksheet, we're going to write out the electron configuration for 4 elements, and we're going to use something different called orbital notation. You don't really need a definition of that. You'll learn to recognize it and see how it's different than just standard electron configuration. Now for orbital notation, it gives us a little bit more information about the electrons, but it starts out kind of the same. For helium, we know it has 2 electrons. Now we know those 2 electrons would end up on the 1s energy level, and sometimes you see it as a blank, other times you'll see it as kind of a box, so I'm going to draw it with a box just one time today. And the thing about these electrons is they're going into the same orbital. And something I haven't taught you yet is that electrons actually have a spin. And the 2 electrons that go into the same orbital, they always have opposite spins. Now you could really think about those spins as being like clockwise and counterclockwise, but they are opposite of each other. And we abbreviate them with arrows. So I'm going to put an up arrow for one, and then the down arrow for the other electron. And this is called the Pauli exclusion principle. Get this into your worksheet. I left you some room off on the side of the page. The Pauli exclusion principle says that none of the electrons in an atom can be exactly identical. So if 2 electrons are sharing an orbital like they are here, one is always going to be an up spin and one will be down. If you've got that, let's go ahead and move on to nitrogen. That's got 7 electrons. And so I'm going to put the first one on the 1s level. So that's 1, and then it's actually going to have a second one there as well. It gets me to 5, so that's going to go on the 2s level. We'll have 1 there, up, 1 down. That gets me down to 3 electrons, and so those go onto that 2p level. But we have to draw in 3 orbitals. Remember the s sublevel, there's only 1 orbital for each s, but p has 3 orbitals. Now a new thing here, get this into your notes, we have an idea to deal with called Hund's rule. And it says if you have more than 1 orbital on a sublevel, you're going to fill each halfway before you pair the electrons together. Let me show you the way that would be wrong. This would not be Hund's rule if you were to fill in this one and then put the third one right here. Hund's rule says we need to fill each orbital exactly halfway before any of them get filled up. But we're not going to do that because we just ran out of electrons. Now I want you to try the next 2 problems on your own, and I promise you that nothing else is going to show up on the screen in this area. So if you need a little more room for one of these that's a little bit larger, don't feel like you have to cram it in. You can use all of this space right here. All right, there are the answers to the other 2. Make sure you check your work, especially this Hund's rule right here where it showed up down here, that each of these orbitals needs to be half full. Now, if anything's confusing about the answers, be sure to ask me in class. I'm happy to help. But if you've got everything correct, well, we're all done with the practice problems. I hope the video has been helpful to you today, and as always, thanks for watching.